Hello, welcome to my channel. In this video, I'll be talking about gas laws, which is an important topic in JAMB UTME syllabus. Gas laws describe the behavior of gases in terms of pressure, volume, temperature, and the amount of gas. And these laws are basic, they are foundational in understanding the properties and behavior of gases in chemistry and physics. Gas law apply to ideal gas. What do I mean by ideal gas? Ideal gas have some properties. There are some assumptions that's is said to apply to ideal gas. You can watch my videos on kinetic theory of matter. What are the assumptions in ideal gas? Assumption in ideal gas is that their molecules have negligible volume compared to their container. There is no force of attraction between molecules, and also molecules move in random motion and collide with each other in elastic manner. These are the assumptions for ideal gas. And when gas doesn't have all this, it's not an ideal gas. All real gases behave like ideal gas at low pressure, and at they behave like an ideal gas at low pressure and high temperature. Okay. At high pressure and low temperature, they behave they divide from the behaviors of ideal gas. I'll start with Boyle's law. And Boyle's law states that at constant temperature, the pressure of a gas is inversely proportional to its volume. So mathematically, this can be represented as volume is inversely proportional to the pressure. And this will become like this, okay? And Vp is equals to K, meaning that at every point in time, when temperature is constant, product of volume and pressure of an ideal gas is constant. And from this, you can derive the formula V1 P1 is equals to V2 P2. This relationship can be expressed diagrammatically, like let's assume like this, which shows that as the volume decreases, the pressure increases. Okay. Graphically, this relationship can be represented like this when a volume is plotted against the pressure. There's inverse relationship between them. You get an hyperbolic curve. Okay, but you can get a straight line if the inverse of pressure is plotted against the volume. You get a straight line like this, or if the inverse of volume is plotted against the pressure, you get this like this. And also, if you plot the products of pressure and volume against the pressure or the volume at every point in time, it gives a straight line. It's constant. Okay. The next law we'll talk about is the Charles law, which states that the volume is directly proportional to the temperature, and this can be evaluated as this, in which K is the constant, and this can become V over T is equals to K. And from there, you can derive this formula. V1 over T1 is equals to V2 over T2, provided the pressure is constant. And graphically, diagrammatically, you can represent this like this. Let's say this, okay, as volume decreases, pressure decreases. Sorry, as volume decreases, temperature decreases because there is direct proportional relationship between them. Okay, and graphically it can be represented like this. When you plot the volume against temperature, it gives a direct a line like this, and that is provided the temperature is in Kelvin. If the temperature is in degrees Celsius, if you plot the volume against the temperature in degrees Celsius, you get this line in which the line will touch the temperature axis at minus 273, okay, degrees Celsius. Okay, so take note of all these graphs because you can see it in exam. The next law I will talk about is the Avogadro's law, which states that the volume of a gas is directly proportional to the mole of the gas, and this can be expressed as V is equals to K N. And this K is the volume occupied by a gas as by 1 mole of gas at standard temperature and pressure which is given to be 22.4 dmq. The ideal gas law combines all these laws that we have talked about. The volume is directly proportional to the temperature as said by the Charles and inversely proportional to the pressure. Okay, and also Avogadro's law says that it's directly proportional to N. Okay, so this can be expressed as this V is equals to R T N all over P. Okay, so this R is called the gas constant, and the value will be given when you are asked question about it in the exam. This formula can be evaluated as Vp is equals to nRT, and this is ideal gas equation. The compressibility factor is derived from the ideal gas equation, which is PV is equals to nRT that I spoke about earlier, and the compressibility factor is equals to nRT over PV. This compressibility factor is usually used to predict how close a gas behavior is to the ideal gas. And the value, when the value, the compressibility factor is 1, is an ideal gas. If it is, if the compressibility factor is not equals to 1, it means this is not an ideal gas. Okay, so now if the compressibility factor is less than 1, it means this gas is compressible. Okay, and at this point the force of attraction between molecules predominates. Okay, force of attraction predominates at this point. Okay, and if the compressibility factor is greater than 1, it means this gas is not compressible. Okay, and that is due to the fact that the repulsive force between molecules predominates at this particular point in time. The graph for the ideal gas equal for an the compressibility factor for an ideal gas when plotted against the pressure at a given temperature is usually a straight line. Okay, and it's usually intercept with the compressibility factor at intercept 1. The real gas, actually their curve is usually like this. Okay, molar volume of a gas and atomicity. The molar volume of a gas refers to the volume occupied by 1 mole of a gas, and it is given to be 22.4 dmq, and this is at standard temperature and pressure. Standard temperature is equals to standard temperature is equals to 273, and standard pressure is equals to 180 m. So we can derive from our ideal gas equation formula, which states that PV is equals to nRT. Since we are trying to check what will be the volume of 1 mole of a gas, N will be equals to 1, and the constant, this constant is called the gas constant, and it is given to be 0.82. So times the standard temperature, which is 273, okay, is equals to volume at 180 m, which is the standard pressure. If you evaluate this equation, this V will give you 22.4, okay, with this unit. Dalton's law of partial pressure tell us about the the total pressure of a gas mixture is equals to the volume to is equals to the sum of the partial pressure of each of the gases, and this usually apply to mixture of gases that are not chemically combined together. Okay, and don't forget to calculate the partial pressure of each gas is usually a percentage composition of each gas, okay, times the total pressure. Okay, now if a gas is collected over water, you need to take into account that water is a volatile matter, and it can also contribute to the total pressure of the gas. So if you are given in a question the the vapor pressure of water at a particular point in time when the gas is collected, you need to take it into account. So the total pressure of a mixture of gas is equals to the total pressure is the partial pressure of the first gas plus partial pressure of second gas, etc. like that. Gay-Lussac law of combining volumes states that at constant temperature and pressure, the volumes of gas reacting at constant temperature and pressure are in whole number. What does this mean? It means when two gases react, let's say hydrogen and oxygen to give water, they usually do so in simple ratio. You see, if you balance this equation, that will give you this. So this is in 2:1. And also to the products, okay? If the product to is gas, it will also be in simple ratio of whole numbers. So you need to take note of this. That's Gay-Lussac law. Graham's law of diffusion tells us how the rate of diffusion of gas, and it states that the rate of diffusion of a gas is inversely proportional to the square root of its molar mass, or to the inversely proportional to the square root of its density. Okay, and this can be expressed mathematically as R is equals to K over root of M. So R root of M is equals to K. So this can give a formula which is R1 root of M1 is equals to R2 root of M2. And this you can use to calculate the rate of diffusion of a gas when one of the gases is given and the molar mass is also given. Now, the units that's commonly used for the calculations in gases, let's talk about them briefly. Usually, volume is usually given in mil, and 1 mil is equals to 1 cm cube. And don't forget that 1000 mil is equals to 1000 cm cube. Okay. And to convert this cm cube to dm cube, to convert centimeter to decimeter, you divide by 10. But since this cube is there, you have to divide by 1000. So 1 dm cube will be equals to, since this is 1000 mil, 2 to be equals to 1000 mil. And don't forget that this is equals to 1 liter. So 1 liter will be equals to 1 dm cube. So take note of this conversion. Pressure, it can be given as atm, and 1 atm atmospheric pressure is usually equals to 760 millimeter of mercury. Take note of that. And for temperature, if you are given in degrees Celsius, you add 273 to it to give you Kelvin. Okay, so take note of that. Having talked about all these laws, we'll briefly talk about, we treat some questions to apply the volumes, the several formulas that we have derived to test our knowledge. Let's start with this question one. A sample of gas occupies 4 liters at 1.5 atm atmospheric pressure. What will be the volume if the pressure is increased to 3 atmospheric pressure while keeping the temperature constant? When so in this one, if you can recall for formulas, the equation you'll be using is the Boyle's equation, which is V1P1 V1P1 is equals to V2P2, and V1 is equals to 4 times P1 1.5 is equals to V2, which we want to calculate, times P2 3. So V2 is equals to 4 times 1.5 divided by 3. Here 1, here 2, here 1, here 2. So the volume will be equals to 2 liters. The correct answer is A. Which gas law helps determine molar volume of a gas? If you recall very well, Charles is, Boyle's is, and Dalton is partial pressure. Avogadro's law tell us what 1 mole of a gas will occupy at standard temperature and pressure. So this is the correct answer, B. When this is less than 1, usually compressibility factor is represented as Z. Okay, so this is compressibility factor. Compressibility factor, and I talk about it in one of the in the compressibility factor section. I said that when the compressibility factor is less than 1, it means the gas is compressible. At that point, the force of attraction between the molecules predominates. Okay, now the question is, when Z is less than 1, the gas is behaving ideally. That is not true, because ideal gas doesn't usually have force of attraction between the molecules. So this is not correct. It's more compressible than an ideal gas, which is true, because at that point, force of attraction between molecules predominate. It's less compressible than an ideal gas. This is false. It's more compressible than an ideal gas. Has no deviation from an ideal behavior. That is false, because at this stage, it has already deviated from ideal gas. That is because in ideal gas, the force of attraction between molecules are negligible, while in this case, the force of attraction between molecules is high, because the Z score, which is the compressibility factor, is less than 1. Graham's law is most applicable to A. Ideal gases only, that is not stated in the Graham's law. Gases at low pressure, that is not stated. Gases at high pressure, that's not stated. Gases that do not react chemically, this is correct, because it tells us about diffusion. If the gases react chemically, they don't obey Graham. So go through each of the questions and try to answer it. You can write your answer in the section below under the comments. Let's open up discussion so that we can learn more. Okay. If you like this video, if you enjoyed this video, like, subscribe, and share so that others too can benefit. As you go through each of these questions, take your time, pause the question, read it very well, and write your answer in the section below. Thank you very much. Don't forget to like, share, and subscribe. I'll see you in the next video. Bye bye.